Dr. Baliga here. This podcast belongs to a group of 10 podcasts on statistics in medicine. These podcasts should give you a solid foundation on this topic. It's derived from an outstanding chapter titled Statistics in Medicine in Baliga's textbook of internal medicine, available at www.mastermedfacts.com. The chapter is authored by Dr. Donna Windish, MD, Associate Professor at Yale University School of Medicine. She is the Associate Program Director for the Yale Primary Care Internal Medicine Residency Program. Dr. Windish completed her medical school degree at the University of Connecticut and her internship and residency in New York at the University of Rochester. She went on to do fellowship in general internal medicine at Johns Hopkins University School of Medicine and obtained her MPH at Johns Hopkins Bloomberg School of Public Health. Dr. Windish has been on faculty at Yale since her fellowship. She is clinically active in both inpatient and outpatient medicine, oversees the research and residency program for the Yale Primary Care Training Program, and teaches medical students and residents biostatistics and how to read medical literature. Multiple choice question. A prospective study looked at renal protection from contrast dye using pre-procedure high-dose N-acetylcysteine, low-dose N-acetylcysteine, or saline prior to the contrast procedure. Which analytic method would be used to test the following hypothesis? Mean serum creatinine level does not vary across three pre-treatment groups. A. T-test for comparing two population means. B. Analysis of variance, ANOVA. C. Correlation analysis. D. ChiSquare test of homogeneity. And E. Logistic regression. And the answer is B. Analysis of variance, or ANOVA. This analysis is comparing an outcome that is continuous, that is serum creatinine for three groups. Thus, given the choices, the best answer would be to use ANOVA, which compares mean outcomes of three or more groups. Of note, the outcome should be normally distributed in order to use ANOVA. Data distributions. Understanding how continuous and ordinal variables are distributed with respect to frequency of outcomes dictates which types of statistical tests are used to make comparisons. The shape of the distribution of outcomes helps to determine whether outcomes are normally distributed and thus whether parametric tests can be used in data analysis. Normal parametric distribution. The normal distribution is a probability distribution used to describe continuous and some ordinal outcomes in a population. It is described as a symmetric bell-shaped curve in which the mean, median, and mode are the same as shown below. Non-normal non-parametric distribution. A non-normal distribution is a probability distribution of continuous or ordinal values that are not symmetric, that is not bell-shaped. Positively skewed data are distributed such that a greater proportion of the observations have values less than or equal to the mean, that is, more observations with lower values. Negatively skewed data are distributed such that a greater proportion of the observations have values greater than or equal to the mean, that is, more observations with higher values. Confirmatory data analysis or inferential statistics. Confirmatory data analysis or inferential statistics uses estimation and hypothesis testing to assess the strength of the evidence, make comparisons, make predictions, and draw conclusions about a population based on sample data. There are two main categories of inferential statistics: bivariate and multivariable analysis. Bivariate analysis investigates the relationship between one dependent, that's the outcome, and one independent, that's the predictor variable. Bivariate analysis includes discrete data analysis and continuous data analysis. Multivariable analysis investigates relationship between one dependent and multiple independent variables while controlling for the possible confounding influence of several independent variables on the dependent variable. The results of inferential statistics are reported according to the type of data collected and the statistical test or method used to determine the result. Bivariate analysis, discrete data analysis, contingency tables show the individual responses to one variable as a function of another variable. The response to a treatment could be categorized according to the treatment type received. Contingency tables are used to calculate relative risks and used in ChiSquare analysis. ChiSquare analysis is a statistical test used to compare two unpaired independent samples where the outcome is dichotomous or nominal and the sample size is large, that is greater than 30. If any cell of the contingency table contains a value of less than 5, Fischers' exact test must be used. The chi-square test itself compares what is observed in the data to what is expected to happen. This analysis starts with the contingency table to display and compare results. You can use chi-square analysis to test independence, that is, two factors are independent, that is not related. To test of no association, that is, two groups are similar with respect to some characteristic. Results of chi-square analysis results are reported as proportions, that is, a number and percentage in each group. Fischers' exact test compares two unpaired, that is, independent samples where the outcome is dichotomous or nominal and the expected sample size for one category is small, that is, less than 5. It is the alternative to chi-square test when results are small. Results of Fischers' exact analysis are reported as proportions, that is, number and percentage in each group. Relative risk assesses if exposure is associated with the change in risk of an outcome. It is one of the most commonly reported outcomes in literature. Results of relative risk are reported as a ratio with a confidence interval. Example, relative risk equals 1.5, 95% confidence interval 1.2 to 1.8. The interpretation is there is a 1.5 times greater risk in group 1 compared to group 2. Alternatively, you can say that the group 1 has a 50% increase in risk compared to group 2. Odds ratio compares the odds of an event happening in one group to the odds of the same event happening in another group. Odds ratios are commonly presented in medical literature. Specifically, they are used in multiple logistic regression analysis when the outcome is dichotomous and the researcher wishes to control or adjust for potential confounding factors. Reporting of odds ratio. Results of odds ratio are reported as a ratio with a confidence interval. Example, odds ratio of 1.5 with 95% confidence interval from 1.2 to 1.8. The interpretation is there is a 1.5 times greater odds of the event in group 1 compared to group 2. Alternatively, you can say that group 1 has a 50% increase in odds compared to group 2. Odds ratio as an estimate of relative risk. When outcomes of interest is rare, relative risk is nearly equal to odds ratio. When the outcome of interest is not rare, relative risk is not equal to odds ratio. The key point is odds ratios are used in certain regression analysis and the results should be described as an odds ratio or change in odds and not as a change in risk. Continuous data analysis. Continuous outcomes and some ordinal outcomes with multiple categories are analyzed using parametric or nonparametric statistical tests depending on the shape of distribution of the outcome variable. Thus, researchers should plot a frequency histogram to assess the normality of data. Each parametric statistical test has a corresponding non-parametric counterpart. When comparisons of means between two unpaired or independent groups are made, the parametric test is student t-test and the non-parametric test is the Wilcoxon rank sum test. When the comparisons of means between two paired that is dependent groups are made, the parametric test is a paired t-test and the non-parametric test is the Wilcoxon sign rank test. When comparisons of mean between three or more independent groups are made, analysis of variance or ANOVA is the parametric test. The non-parametric test is the Kruskal-Wallis test. Parametric statistical tests assume that the distribution of outcome variable is normal or bell-shaped. These tests are used when evaluating continuous or ordinal variables that fit a curve with a normal distribution. There are three parametric statistical tests: student t-test, paired t-test, and ANOVA. The key point is, while there is no absolute sample size that one can rely on to definitely use a parametric test, continuous or ordinal outcomes on sample sizes greater than 50 may be considered strongly for parametric test. A student t-test is a statistical test used to compare two unpaired or independent samples having a normally distributed continuous outcome. Unpaired or independent means that the groups are not related to each other in any way. For example, in a randomized controlled trial where patients are admitted to a study to assess efficacy of a new drug, there is no dependence or pairing of one patient to another. Instead, these patients are randomly chosen in the study and are then randomly assigned to one or another study groups. Note, the student t-test is also known as a t-test or an unpaired t-test. Reporting of student t-test results, they are reported as the mean difference between groups with a standard deviation or standard error. Paired t-test is a statistical test used to compare two paired or dependent values where the outcome is continuous and normally distributed. These pairs can be the same individual before and after an intervention or exposure, or they can be two different individuals who have a common origin. For example, individuals could be A, twins, that is common genetic origin, B, family members who live together, environmental common origin, and C, matched cases and controls in a case control study matched by some characteristic. A paired t-test uses the differences between each of the pair of outcomes in the final analysis. Reporting of paired t-tests. Results of paired t-tests are reported as the mean difference between a pair of groups or before and after an intervention with a standard deviation or a standard error. ANOVA. The ANOVA is the analysis of variance, compares the differences in means of a continuous outcome variable with the normal outcome distribution when three or more groups are compared. Results of ANOVA are reported as mean differences between groups with a standard deviation or standard error. The key point is the p-value given in an ANOVA represents the statistically significant difference between all groups being compared and not individual comparisons between any two groups. Thus, the only conclusion one can make from this test is that at least one of the groups is different from rest of the groups being compared. Non-parametric statistical procedures rely on few or no assumptions about the shape or parameters of the population distribution from which samples are drawn. These tests do not assume that the shape of the distribution is known. Thus, they are more conservative tests. These tests should be used when the outcome has a non-normal distribution or when the sample size is small. Three main non-parametric statistical tests are the Wilcoxon rank sum test, the Wilcoxon signed rank test, and the Kruskal-Wallis test. The key points are: non-parametric tests are statistically less powerful than parametric tests, thus they are less likely to show a statistically significant difference when one exists. Non-parametric tests often use rankings when reporting results and not actual data. This can make the interpretation more difficult. Wilcoxon rank sum test. The non-parametric statistical test compares two unpaired, that is independent samples where the outcome of interest is ordinal or continuous and not normally distributed. The Wilcoxon signed rank test. This is a non-parametric statistical test which compares two paired, that is dependent samples where the outcome of interest is ordinal or continuous with a skewed distribution. And the Kruskal-Wallis test is used to compare differences in a continuous variable when three or more groups are being compared and have a non-parametric outcome distribution. When the Kruskal-Wallis test leads to significant results, then at least one of the groups being compared is different from the other groups. This test does not tell us which group is different. Reporting of non-parametric results. The three non-parametric tests calculate the level of statistical significance based on weighted values and not the actual values observed. Results should be reported by the researchers as medians with interquartile ranges. Multivariable regression analysis. Regression analysis is a statistical method used to describe the association between one independent variable and one or more independent variables. It is used to adjust or control for confounding variables. It can also be used to predict or estimate the value of one variable based on the value of other variables. A confounding variable is a variable related to one or more of the variables in a study. This variable may mask an actual association or falsely demonstrate an apparent association between the study variables where no real association exists. A variable is a confounder if it is related to the predictor variable and the outcome variable, and it is not in the causal pathway between the two variables. Some examples of common confounders are age, gender, and other comorbidities. Example of confounding is when, for example, obesity causes both diabetes and heart disease. So it can be a confounder on whether diabetes causes heart disease. Linear regression. Linear regression analysis is used to quantify the association between one or more independent variables and a continuous outcome that is normally distributed. Depending on the number of factors being compared, one can use a simple linear regression or a multiple linear regression. Simple linear regression is a comparison between one independent and one continuous dependent factor. It does not control for potential confounding variables. For example, comparing exercise as it relates to blood pressure, where exercise is the independent variable and blood pressure is the continuous dependent variable. Multiple linear regression is a comparison between more than one independent and one continuous dependent factor while controlling, that is adjusting for potential confounding factors. For example, comparing exercise as it relates to blood pressure while controlling for age, weight, and smoking status. In order to decide what factors to control for any type of regression analysis, researchers analyze, that is control for, factors that are A, significant in simple regression analysis, B, are previously known to confound results, and C, make sense as confounders. The key point is, only multiple regression controls for confounding factors. Simple regression is used to assess which factors are independently associated with the outcome of interest. Reporting of linear regression results. The outcome for a linear regression analysis is expressed as a B coefficient. This coefficient is the expected change in an outcome when the predictor variable changes by 1 unit and other variables, that is confounders, remain fixed. For example, the mean change in blood pressure by 5 millimeters of mercury in the exercise group compared to the no exercise group after controlling for age, gender, and other medications. Logistic regression. Logistic regression analysis is used to quantify the association between one or more independent variables and a dichotomous outcome. Depending on the number of factors compared, one can use a simple logistic regression or multiple linear regression. Simple logistic regression is a comparison between one independent and one dichotomous dependent factor or outcome. For example, comparing independent variable as it relates to mortality, which is a dichotomous dependent variable. Multiple logistic regression is a comparison between more than one independent and one dichotomous dependent factor while controlling for potential confounding factors. For example, comparing exercise as it relates to mortality while taking into consideration age, weight, and smoking status. Logistic regression results are reported as an odds ratio with a confidence interval. For example, the odds ratio of mortality for subjects who exercised compared to those who did not exercise was 0.35, 95% confidence interval, 0.10 to 0.54. This can also be stated as subjects who exercised had a 65% decrease odds of mortality compared to those who did not exercise. This podcast on statistics in Journal Internal Medicine is derived from an outstanding chapter on this topic in Baliga's textbook of internal medicine, available at www.mastermedfacts.com. It's authored by Dr. Donna Windish, Associate Professor in Internal Medicine at Yale University School of Medicine.